So continuing in 6.1, we at the end of last class came up with two methods for solids of revolution, right? If the region happened to be flush up against its axis of revolution, what we generated was a solid sliced by disks. So we had the disk method. And what's the area of a circle? Pi r squared, pi times radius squared. If, however, it was not flush up against it, when we revolved it around, there was a hole in the middle. So instead of having disks, we had washers as cross sections. And what's the area of a washer? Pi big R squared minus pi little r squared. Again, the pi is in common. I can factor it out. So we wind up with pi, and then it's that outer radius squared minus that inner radius squared. All right? So these are our two methods so far. Now we're going to have one more method we add on top of this, but not for this section. So let's do some examples of these two to get us started. So let's say that we have a region bounded by x equals y to the 3/2, x equals 0, y equals 2, and we revolve this about the y-axis. So that's our axis of revolution. All right? So let's just picture the region to get us started. I'll scale by halves. All right. Now, let's talk about where these intersect. All right. There's three of them, but two of them are really easy. X equals 0 is vertical and y equals 2 is horizontal, right? So obviously 0, 2 is one of the intersections. All right. If I plug in x equals 0, 0, 0 is another intersection. You guys agree? If I plug in y equals 2, then we get x equals 2 to the 3/2. That's 2 root 2, isn't it? Wouldn't that be 2 root 2? Which is what, 2.8? So when y was 2, x was 2.8. So here's the horizontal line y equals 2, the vertical line x equals 0, and then we have that graph x equals y to the 3/2. Like so. Do you guys see how I graphed this region? Then we revolve this region around the y-axis. Right? So if I were an artistic fellow, which I'm not, right, then I could draw a beautiful three-dimensional shape. As it is, you're stuck with me. So this is what that shape's going to look like. Now imagine if I spin it, the top is going to make a circle, right? You're going to have a flat circular top, and it's going to be pulled in like so. So we made a tornado. That's kind of awesome. All right. Now, here's my question to you. How do you want to slice this? Horizontally is a wise choice. All right. So let's think about this. I'll draw a little horizontal slice. Imagine that little slice being spun around the axis of revolution. What is it going to make? It's going to make a disk. So there's the 3D example of what happened when we spun that around, right? What if I tried to slice vertically? You guys are pretty good not to choose that. Well, take that vertical slice. If you spin that around the y-axis, you're not making a disk, right? You're not even making a washer. You're making a ring, aren't you? Like a ring for your finger. That's a different method. So we'll have to talk about that later. All right? Okay, so if this is what we're going with, Then what is your thickness? dy. And that means everything else about this integral is going to be in terms of y. Since it's a disk method, the only thing we need is the radius of those disks, right? The radiuses that we're creating. Well, doesn't this little blue line we drew represent a radius of that disk? So how would I get that length? So y to the 3/2 minus 0, which would be right minus left. You guys agree? Again, it's got to be in terms of y, because you chose the thickness of dy. Is that all right? And this is x equals y to the 3/2, and this is x equals 0. So volume. If we're using the disk method, it's pi r squared, right? Pi radius squared. So pi radius would be y to the 3/2 squared times thickness dy. Do you guys see how I put that together? Pi r squared. What about my limits of integration? They must be x or y values. They must be y values. So from where to where? From 0 to 2. Is everybody okay with that? So we wind up with pi, integral from 0 to 2, y cubed dy, because the square root and the square will cancel out, right? The half power and the 2 power. And luckily enough, this is fairly easy to integrate. One quarter y to the 4th. You guys agree? So there's a pi out front. Let's not forget about pi. And we're going from 0 to 2. So I have pi fourths, and then that would be 2 to the 4th is 16. And if I plug in 0, I zero out the back half. You guys agree? So what do we wind up with? Four pi units cubed. The volume of that tornado, 4 pi cubic units. It's not a big tornado. It's a little mini one. Well, okay. That's actually a very good point. Someone's engineering minded. All right, let's try another one. What if I gave you y equals e to the x minus 1, y equals 0, x equals 1, and x equals 3. And we revolve this about the x-axis. All right. So let's see. We actually have 4 equations, but again, 3 of them are really, really easy. All right? I mean, fingers crossed. I don't know what you guys think, but I think they're really, really easy. So let's see. If I look at 1, 0, and 3, 0, and 1, 3, those intersections were all really easy, right? Almost so easy it's hard. Y equals 0, x equals 1, that's 1, 0. Y equals 0, x equals 3, that's 3, 0. Oh, 1, 3 is not on there. I just made that up. You're just going to let that fly, huh? Now, I do need to plug in to find these intersections. If x equals 1, then what do I get for y equals e to the x minus 1? 1. So that's going to be 1, 1. There we go. And if I plug in 3, that's going to be e squared. What is e squared approximately? And I don't have that one off the top of my head. It's going to be maybe 7 point something.
7.3, 7.4.
There we go, 7.4 approximately. All right, if I tried plugging in y equals 0, an exponential will never equal 0, so that doesn't have an intersection. So we've got x equals 1, y equals 0, x equals 3, and then the exponential function makes a curve like that, right? Is this okay? So here's our region, and we are revolving it around the x-axis. All right, so if I spin this around, I'm going to get a little circle on the left, and I'm going to get a big circle on the right. Looking like this. I don't know, a bullhorn. Why not? How do you want to slice this?
Vertical.
If I slice vertically, so picture that little vertical bar. As it spins around the x-axis, what kind of shape will it generate? A disk. All right, we'll generate a disk, which is fine for now. If I tried to slice horizontally, picture a horizontal bar. If you revolve that around the x-axis, what does it generate? A ring. We're not ready for rings yet. All right? It's kind of fast if you ask me. So, what is our thickness? Yeah, I mean, you have a 50% chance of guessing right if you know nothing. Right? Hopefully you know a little more than nothing. dx is right. That's infinitesimal value of x width, so its thickness is dx. That means everything else about this is going to be in terms of x. Now, since we're making disks, the only thing that matters there is the radius, and that blue line represents the radius of that particular disk if I spin it around, right? And what is that blue line? E to the x minus 1 minus 0. This is y equals e to the x minus 1. This is y equals 0. Top minus bottom, right? Big minus little. In this case, that means top minus bottom. So volume, pi r squared. Pi, radius is e to the x minus 1. Squared dx. You guys agree? What about my limits of integration? Are they y values or x values? Yeah, they got to be x values here. So from what to what? From 1 to 3. You guys feeling really confident about those limits? Okay. I mean, I wrote it down, so that's a good hint, right? So you get pi times the integral from 1 to 3, and that would be e to 2x minus 2 dx, power raised to a power raised to another power, right? Base to a power raised to another power. You multiply the powers together. So 2x minus 2. Can we integrate that? Fingers crossed. So what's the antiderivative of e to its power? Itself. So that's e to the 2x minus 2. However, this would have involved a chain rule of 2. So I got to reverse that. So what do? Divide by 2. So pi over 2, e to the 2x minus 2. That's the antiderivative going from 1 to 3. Is that all right? So if I plug in, that's e to the 6 minus 2, which is 4, minus e to the 2 minus 2, which is 0, right? So I wind up with pi halves times e to the 4th minus 1. That is your exact volume. Now you could get a decimal approximation if you were asked, but this would be the exact volume. Is that okay? Not so bad, maybe? After I brutalized you last time, now you're finally starting to become accustomed to it. Well then, how about I throw some trig at your face? You knew it was coming. Right? Let's say that we have y equals 2 sine x, y equals 2, x going from 0 to pi halves, and we spin about the y-axis. All right. Now, y equals 2 is just a horizontal line. X equals 0 and x equals pi halves would just be vertical lines. So once again, 3 of those are super easy. The only one, y equals 2 sine x, right? So let's see. I've got zero, 2, x equals 0, y equals 2. And pi halves. Oh, let's change this. Instead of the y-axis, let's do y equals 2. Right? That's going to be a little bit nicer. We'll wait to level up. All right, so again, we wind up with 0, 2 here. We've got pi halves. Pi halves is a little over 1, right? What's pi halves approximately? 1.6. Sure. So there's 1.62. So there's y equals 2. There's x equals 0. And of course, how does the sine wave work out of the origin? You guys agree? Sine wave. Ooh, remember that good old friendly shape? Burned into your left eyelid, right? This time, though, our axis of revolution is the line y equals 2, all right, which actually makes this a nicer question. So, if I were to picture this three-dimensional shape, keeping in mind I'm spinning this region about the line y equals 2, I would have a big circle on the left. Oh, so it's a sideways tornado. Those happen sometimes. And how do you want to slice it?
Vertical.
Yeah, vertically is the better choice. Picture that vertical slice. As you spin it around that line y equals 2, what are you generating? A disk, right? If you tried to slice it the other way, horizontally, you would generate rings, right? I keep proposing to you, but it's not happening yet.
So it's always perpendicular to the axis you're spinning it on?
For now. That sounded ominous, didn't it? So what's your thickness? Dx, right? It's a dx thickness. And since we're making disks, the only thing that's important about a disk is the radius, right? Now, what you want to keep in mind is that we're no longer spinning around one of our axes, the x-axis or y-axis. We're spinning around the line y equals 2. So if I try to come up with the radius, which this blue line represents, what is it going to be?
2 minus 2 sin x.
Yeah. Two minus 2 sine x. Do you guys agree? Right. Top minus bottom in this case, since that's what big minus small means for vertical slices. 2 minus 2 sine x. Is everybody okay with that? All right. Then we're ready to put together volume. So it's pi r squared, pi radius squared, where a radius is 2 minus 2 sine x, and then dx. That's your thickness, right? Area times thickness is volume. What about my limits? 0 to pi halves. They got to be x values, right? Are you guys with me on that? 0 to pi halves. All right, so we'll do out the square. So we got pi times integral from 0 to pi halves. That would be 4 minus 8 sine x plus 4 sine squared x. You guys agree? Can I integrate these? What's not integrable? Yeah, we can't deal with sine squared. So what do we have in our repertoire? Nope. You don't have to go that far.
Do we know integration by parts yet? Or?
No, that'll be Calc 2. You have in your handout power reduction formulas. Dun, dun, dun. Okay. So, for example, sine squared of x is 1/2 1 minus cosine of 2x. Or you could think of that as 1 minus cosine of 2x all over 2. And in fact, that's essentially your half angle formula squared. You saw this if you were my trig student when I went through the half angle formula development. I told you in calculus it'd be back. Here it is. All right. So I'm going to substitute that in for sine squared. So this means I've got pi, integral from 0 to pi halves, 4 minus 8 sine x, and then 4 times that power reduction formula is going to make that 2 minus 2 cosine 2x, right? Because half of 4 is 2, right? And then I can distribute the 2. Like terms? Why, yes, don't mind if I do. 6 minus 8 sine x minus 2 cosine 2x dx. All right, so no calculus yet. This has all been using a trig identity and combining like terms. All right. Can I integrate now? Yes. Now we can go ahead and integrate all of these pieces. So I've got one lonely pi out front, and then the antiderivative of 6, 6x, minus 8 sine x becomes plus 8 cosine x. Derivatives of c's are negative. So antiderivatives that come out c are negative. That means antiderivative of sine is negative cosine. What about minus 2 cosine 2x? Antiderivative there. Antiderivative of cosine is sine, right? So the sign won't change, SIGN. And then wouldn't there have been a chain rule there? Chain rule of 2, which I counter by using a half. Half of 2 is 1. Is that okay? You can use a baby U substitution on those, but your book introduced these basic chain rule reversals before U substitution. So your book has expectations of you. Okay. Me, All right, so let's see what happens when I plug in. So I've got pi, that's going to be 3 pi plus 0 minus 0, because cosine of pi halves is 0, and sine of pi is 0. Minus, that's going to be 0 plus 8 minus 0, because cosine of 0 is 1, sine of 0 is 0. So we wind up with a volume of pi times 3 pi minus 8 cubic units. Is that okay? Yes.
Okay, so if we're rotating it, are we finding the area under the curve, or we're finding the shape we're making when we're rotating it?
We are finding the volume of this beautiful artwork right
Okay,
here.
So that's why it's cubes. This is 3D.
Mm-hmm.
Okay.
Yes. Cubic units for volume. All right. All right, let's try another one. All right. We're going to be spinning so much your head will be spinning. It will be a solid of revolution. All right, that was bad even for me. All right, I don't even blame you for not laughing. But to punish you for it, I'm going to throw more trig at you. So let's say that we look at y equals secant x, y equals tangent x, x equals 0, x equals 1, and revolve this about the x-axis. All right. Oops. Why freehand it? That's just asking for trouble. All right, so let's say I scale by thirds, because I can. So if I plug in 0 to each of these trig functions, tangent of 0 is 0, so that's 0, 0. Whereas secant of 0 is 1. So that's 0, 1. Because cosine of 0 is 1, and so its reciprocal secant is also 1. Does that make sense? Now, if I plug in 1 into each of those, well, that's not pretty, is it? I get tangent of 1 or secant of 1. That's a real number. It's just not real pretty. Okay. if you want to get just an idea, make sure we're in radian mode. Tangent of 1 is about 1.6. And secant of 1 would be 1 over cosine of 1, right? And that's about 1.8. Now, who is bigger, the secant or the tangent? Secant was bigger. So remember that secant made those cup shapes, right? Whereas tangent made a shape that was very similar to the snake, right? Only we just want the positive portion. So then x equals 0 and x equals 1 make these walls. Is that okay? And we are revolving about x-axis. How do you want to slice it? 50-50 chance you guess right. All right. In fact, you can do it both ways. We just haven't done the other method yet. So really there's no wrong answer. We're just only working with a couple of methods so far. Now, you got to picture it in your mind's eye. If I slice vertically, take that vertical blue line, spin it around the x-axis. What are you going to generate? You're going to generate a washer. Can you guys visualize that? Can you see it? If I had done horizontal, spinning it around the x-axis would generate that ring shape, right? We're going to do washer because we have a formula for it. We'll do rings later. So let's see. If we spin this around, we actually wind up with a circle on the left, and then we wind up with rings. So this is a more legit tornado. Although still on its side, so, you know, a dead tornado. And what that little blue slice turns into is this washer. Right? That inside piece is hollow. Right? That little tornado inside is hollow. So we wind up with a ring for a cross section. Or a washer, sorry. A washer for a cross section. Thickness? dx. Now, for washer, we have two radiuses that we have to concern ourselves with. We have an outer radius, which was the big R, and we have an inner radius, which was the little r. The trick is, how do we know which one is which? Well, it's all from the perspective of your axis of revolution. If I'm spinning around the x-axis, then my outer radius would stretch all the way to the top, right? So what is your outer radius? Secant x minus 0, right? Which is just secant x. Secant x minus 0. What is your inner radius? Again, it's got to come from the center of revolution. Your inner radius would be tangent x minus 0. Which again is just tangent x. Do you see how I got that? Is that okay? From the center of revolution, your outer radius would be secant x minus 0, and your inner radius would be tangent x minus 0. All right? So volume, pi big R squared minus pi little r squared, factor the pi out. Outer radius squared, secant squared x, minus inner radius squared, tangent squared x, dx. You guys agree? Pi big R squared minus pi little r squared. Factor the pi out. What about my limits of integration? They go from 0 to 1. Best limits ever. Can we integrate? Not quite. Which one is the one giving us trouble? Tangent squared. But we have a rule for that. What can I do?
Make it secant squared minus 1. Something like that.
You got it. Right? If 1 plus tangent squared is secant squared, then tangent squared is secant squared minus 1. Right? Now I'm giving you those trig identities, so I have no pity on you with this. Right? You didn't have to remember them, you just have to read them. Right? And you do have to think. I'm not going to apologize for that. All right, so we got pi, integral from 0 to 1. Right? Now, there's a negative that was in front of this, right? So that winds up being one. Secant squared minus secant squared, gone. Minus a negative 1 is 1. You can write a 1 if it makes you feel better. But you don't have to. And this is definitely one of those situations of so easy it's hard. What's the antiderivative? Right? So easy it's hard. Antiderivative is just x. Right? If you take the derivative of x, you get 1 back. Right? From 0 to 1, so we wind up with pi times 1 minus 0, which makes our volume pi cubic units. Is that okay? Not as bad as you were imagining? Maybe as bad as you're imagining? I don't know. Worse? I don't know. What if we attempt y equals square root of x, y equals 2, x equals 0, and we revolve this about the x-axis. Okay. So again, these are fairly simple graphs. Hopefully we don't have to get too hung up on the intersections. Where do we intersect? Yeah, we've got 0, 0. If x equals 0, you definitely get 0, 0 as an intersection. We wind up with 0, 2, not 2, 0. 0, 2, that's where those two intersect. And what about these two? If I plug in y equals 2, 2 equals square root of x means 4 equals x. So that's going to be 4, 2. So y equals 2 is this horizontal line. X equals 0 is a vertical line. And y equals square root of x. I connected all of my dots. I am inordinately proud of myself at this moment.
Will we always be in quadrant one, like that part of the graph, or is it like different parts of the graph?
Your book likes quadrant 1, but it's not necessary to do that. Especially if one of your axes of revolutions is going to be the x or y axis, they're definitely going to favor quadrant 1 heavily. All right? Okay, so in this case, we are spinning about x-axis. How do you want to slice? If I slice vertically, what shapes do I make? Washers. Can you guys picture that? Picture that vertical slice as it slides around. It's going to make a washer, right? If you did horizontal, that would make those rings, right? Right, which I keep tantalizing you with. We'll get there. All right? So let's see. If I draw this, I'm going to get a barrel shape. With like a searchlight shape cut out. Or you know what? It's a shot glass on its side. How about that? And that little blue cross section, what that would represent in 3 dimensions, is this washer. That's the one washer. Of course, it's filled up with infinitely many washers. We're filling this whole shape with these washers. All right, my drawings have just gotten progressively bigger. I have to move that out of my way. What's our thickness? dx. You know a dy is coming. This has been too many dx's in a row. It's like psychological warfare on you guys. So we've got to do the outer radius and the inner radius, right? That's going to come from your center of revolution, where that axis is. So what's your outer radius? Very good. Your outer radius would be 2 minus 0 from that center, right? Your inner radius? Inner radius is square root of x minus 0. Is that okay? So for volume, it's pi big R squared minus pi little r squared. So that's going to be 2 squared minus square root of x squared dx. And I'll factor the pi out. You guys agree? Pi big R squared minus pi little r squared, factor the pi out. What about my limits of integration? 0 to 4. Is everybody okay with this setup? You feeling pretty confident about setting this integral up? So that's pi integral 0 to 4. That's just 4 minus x dx, right? Antiderivative, we got pi out front. 4x minus 1 half x squared. That's going from 0 to 4. So that's a pi out front, and that's going to be 16 minus half of 16, which is 8. And then if I plug in 0, the whole back half zeroes out, right? So we wind up with 8 pi cubic units. All right, let's try a slightly different approach. Let's say a region is the triangle. With vertices 1, 0, 0, 1, 1, 1, and we revolve about the y-axis. Now on the one hand, this will be the easiest picture ever, right? But on the other, that's going to be a little work for the equations. Not much, but a little. So intersection points are almost a moot point. We've got 0, 1, 1, 0, 1, 1. That's going to make a triangle because they said so. And we're revolving around y-axis. All right, so if I spin this around, let me get that barrel again with a cone cut out. Are my three-dimensional drawings actually making a dent? Can you just picture what those are? They look great to me, but you know, I have low standards for drawing. So how do you want to slice that? Yeah, you know, I threatened you last time. If you slice horizontally, picture that horizontal slice. As it slides around the y-axis, it's going to generate a washer, right? It generates a washer. In this case, if I attempted a vertical slice, going around the y-axis would generate rings, right? So your thickness? Is dy, which means everything else has to be in terms of y. Now, we need an outer radius and inner radius. From our center of revolution, right? Now, the outer radius is pretty easy. The outer radius is 1 minus 0. The inner radius, what are we going to need? We need the equation for that line, right? That's where we have to do a little bit of extra work because they didn't give it to us. But that's okay. So what's the equation of that line? How can I get it? Yeah. Probably the easiest way to think of it is in slope-intercept form. What's the slope?
Negative x plus 2.
Yep, the slope is negative 1, and the y-intercept is?
I don't know how it's scaled.
Oh, okay. I scaled by halves, but the vertices up there, 1, 0, 0, 1. So it had a slope of -1 and a y-intercept of 1, so y equals -x plus 1. That's unfortunate because this is a dy integral, meaning I need everything in terms of y. So that means add the x over, subtract the y over, x equals 1 minus y, or -y plus 1 if that's your thing. So what is my inner radius? 1 minus y minus 0. Is that okay? So volume, pi big R squared minus pi little r squared. So that's going to be 1 squared minus 1 minus y squared dx. Pi big R squared minus pi little r squared, factor the pi out. Limits of integration? Oh, it's dy. Thank you. And that's important because my limits of integration are y values then 0 to 1. Is that okay? So we got a pi, we got an integral from 0 to 1. And this would be 1, and then we have minus 1 plus 2y minus y squared dy. You guys agree? If I do out the square, that's 1 minus 2y plus y squared, but there's a negative in front. So that's going to flip my signs there. 1 minus 1? 0. Boy, was there a pregnant pause before you answered, though. So we've got pi times integral 0 to 1 of 2y minus y squared dy. Let's integrate this. So that's a pi and then antiderivative.
Y minus y cubed divided over 3.
Okay. So it's y squared, right? Minus 1/3 y cubed. Or y cubed over 3 is the same thing. If I plug in 1, I get 1 minus 1/3. And if I plug in 0, that 0 is the whole back half out, right? So my answer is 2 pi thirds cubic units. What if I give you x equals y squared, x equals 0, y equals 2, and in the spirit of homework, let's spin about A, the y-axis, B, the line y equals 2, and C, the line x equals 4. So I'm actually going to use the same region here, but we're going to use 3 different axes of revolutions and see what kind of different shapes we generate, and ultimately, of course, what their volumes are. So let's try. That was pretty bad. All right, so again, some of these are easy. We've got 0, 2, we've got 0, 0, and we've got 4, 2. Do you guys see where I got those? There's 0, 2. There's 0, 0. There's 4, 2. X equals 0 is vertical. Y equals 2 is horizontal. And what does x equals y squared look like? It's a parabola on its side, right? Now I'm only using the top half because the other half is going to be not connecting to our region. All right. Now let's explore these different axes of revolution. So for the first one, we're just spinning about the y-axis. Okay. So if that's the case, I'm going to make a tornado again, low and wide, right? You guys agree? How do you want to slice this? If I slice horizontally, my cross sections are going to be discs. Picture that little horizontal sliver. As you spin it around the y-axis, it's going to generate a disc. Do you guys agree? So if this is a disc, your thickness here is dy, and the only thing we have to worry about for a disc is radius. What's the radius for this? Mumble, mumble. Y squared minus 0. Are you guys all confident in that? Right? That little blue line represents the radius of the disk, and that's going to be y squared minus 0, because this is the graph for x equals y squared, and this is x equals 0 on the left.
Where does the 0 come from? It's every radius. It's like y minus 0.
Because it's big minus little, which in this case is right minus left, and the left is 0. All right, so that one wasn't so bad. Volume then is going to be pi r squared, where your radius is, we already did this, I wrote it down, y squared. So radius squared. So y squared squared dy. Pi r squared, pi y squared squared dy. Limits of integration, 0 to 2. Now this is going to be pi integral 0 to 2 y to the 4th dy. You guys agree? And we can integrate this. This one's not so bad. Antiderivative, 1/5 y to the 5th. We have a pi out front. So pi over 5 y to the 5th. Limits going from 0 to 2. If I plug in those limits, that's going to be 32 minus 0. Do you guys agree? Yes? No? Drool? So 32 pi fifths units cubed is the volume of that low, wide tornado shape. Is that okay? All right. I mean, that was part A, so we would hope that was the easiest one, right? For part B, I gave you the line y equals 2. So now we're spinning around the line y equals 2. Same region, but now I've changed my axis of revolution. This time, if I spin as requested, you get sideways tornado, or that looks kind of like a horn. How do you want to slice it? If I slice vertically, my cross sections will be discs. You guys see that okay? Your thickness? Dx. And then for a disk, all we care about is radius. Now, this is x equals y squared, but since we have a thickness of dx, that means my integral has to be in terms of x. So how can I change this equation, solved for y in terms of x? Y equals plus or minus square root of x. Because remember, the whole thing for x equals y squared is a sideways parabola. So if you solve it, y equals plus or minus square root of x, but we're only choosing the positive because it's the positive y values here, above, not the negative ones. Is that okay? So tell me my radius. 2 minus the square root of x. Do you guys agree? These are my representative slice that turns into a disk. It represents radius, and that's big minus little, 2 minus square root of x. Is that okay? So volume, pi r squared. So pi, 2 minus square root of x all squared. Limits of integration, 0 to 4. And I can't integrate that as is, so what do I have to do? Just stare at it until something happens. Pi, integral from 0 to 4. Let's multiply out the square. So that's going to be 4 minus 4x to the 1/2 plus x dx. All right. Talking about intermediate algebra earlier. Can you square a binomial? Fingers crossed. Okay, those we can integrate. So pi is just hanging around. Antiderivative of 4 is 4x. Next, that would be an x to the 3/2, right? So minus 8/3 out front, because we got a 2/3 times the 4 already there. And then plus 1/2 x squared. Now I'm throwing all the ugly fractions at you. We got this. Well, I have it. I don't know about you. We'll see. Pi times. If I plug in x equals 4, I'll get 16. Now, 3/2 power means that's a square root, right? So the square root of 4 is 2. 2 cubed is 8. So that actually winds up being minus 64/3. And then 1/2 of 16 is 8. And if we plug in 0, the whole back half zeroes out. Just love when that happens. It's so satisfying. Just zero it out. And what is this going to be? I hear little calculators tap, tap, tapping. Remember to leave pi off when you do the calculator, but put it in when you actually write your answer. So we basically wind up with 24 minus 64/3, and that winds up with a pi out front, giving me, that's what I got. Eight pi-thirds cubic units. Is that okay? All right, so notice, we took a shape. When we spun it around the y-axis, we generated this low wide tornado with 32 pi-fifths cubic units volume. Same shape spinning around y equals 2 gave me this little horn shape whose volume was 8 pi-thirds cubic units. But I gave you more, right? Now we're going to spin this around the line x equals 4. We're going to spin this around the line x equals 4. So this is going to give me if I take that region and spin it around x equals 4, I get a barrel shape with a little mound cut out. A shot glass turned upside down? Because you just chugged it, right? Okay. How shall we slice this one? All right. Again, in actual practice, both answers are right depending on the shape that you make. But for what we have right now, horizontal is the right choice. And what shapes do we make with those cross sections? We make washers. So there's that cross section. We're making washers out of that little blue sliver. All right. So for washers, what's the thickness for each of these washers? It'll be a dy. And then for washer, we have an outer radius. And we have an inner radius. Now keep in mind, the outer and inner radii come from the center of revolution, right? So, my outer radius is this. From the center of revolution, which is at x equals 4, out to the outer edge of that shape, if you picture it spinning around, the outer edge. And what is that outer radius? 4 minus 0. You guys okay? My inner radius. Again, you got to come from the center of revolution. Now we go from the center of revolution, which is x equals 4, to the inside of the shape, where the hole is cut out, right? So what is my inner radius? Four minus y squared. Right? So if this is my inner radius, right, it's still big minus little, which horizontally means right minus left. 4 minus y squared. Is everybody okay with that? Is everybody all right? Right? So with these washers, volume is pi big R squared minus pi little r squared. And I can factor the pi out. So that's going to be 4 squared minus 4 minus y squared squared. So pi big R squared minus pi little r squared, factor the pi out. 4 squared minus 4 minus y squared squared. dy. Everybody's still on board. Anybody fall off the back of that bus? What about your limits of integration? 0 to 2. All right, they got to be y values, so they're 0 to 2. That wasn't so bad, right? But now we got to multiply all this out, because that's definitely too complicated for a simple rule. So you got pi times integral from 0 to 2. That's going to be 16. Then we have minus 16 plus 8y squared minus y to the 4th dy. So I had to square out 4 minus y squared, which is 16 minus 8y plus y to the 4th, and then distribute a negative 1. You guys with me on that? Simple math. But it never goes away. It just compounds. Actually, before I go ahead and do that, I can still clean up a little bit, because 16 minus 16 is canceling out. Which makes life a little cleaner. So I got pi, and then the antiderivative of 8y squared. 8/3 y cubed. And then minus y to the fourth, we get the antiderivative 1/5 y to the fifth from 0 to 2. When we first started doing these antiderivatives, you were like, those are hard. Now you're turning them out pretty good.
Like nothing but easy ones, this whole section.
Some of them required a little bit more. But yeah, these are going to be a little bit easier on you. Although you get some nasty fractions that you have to deal with. For instance, when I plug in 2, that winds up being 64/3 minus 32/5. At least the back half is 0. And what are you guys coming up with?
224 over 15. 5.
224 over pi over 15 cubic units. Very good. Very good. Just like the homework, how about I spring another piece on you? Same region. This time let's revolve it around x equals -1. All right. So this region one last time goes out with a bang, but we're going to revolve it around the line x equals -1. All right. So if I do this solid of revolution, I'm going to generate a big circle on top that funnels down with a cylinder cut out from the center. Is that all right? So a candle holder. Why not? How about it? I can come up with something for anything. How do you want to slice it? You guys all on board, or are you going to leave those two hanging? If I do horizontal slicing, what generates for my cross sections? We generate washers. Picture that little blue line spinning around, generating a washer. If I had done a vertical slice, we generate the ring shape, which we're almost ready for. So what's your thickness? dy. And then for washer, we have an outer radius. And we have an inner radius, right? Now, you got to come from the center of revolution, which now is over at x equals -1, right? So what is my outer radius? So from that x equals -1 center, I have to go to the outside of the shape, which would be that curved line, which was x equals y squared, right? So it's going to be y squared minus -1. What about the inner radius? My inner radius, again, it's got to be from the center of revolution, which is x equals -1, to that inner wall from where that hole is cut out. So it would be 0 minus -1. So this means my outer radius is y squared plus 1, and my inner radius is 1. You should be able to make sense of this. As you slide up and down that shape, that inner radius is always going to be a 1. You cut a cylinder out, right? The radius won't change. But the outer radius is going to grow as you move up the y-axis. All right. So volume equals pi big R squared minus pi little r squared. So the big radius is y squared plus 1 squared, and the little radius is 1 squared dy. So y squared plus 1 squared minus 1 squared. We factor the pi's out front. dy, limits of integration, 0 to 2. So that's pi integral from 0 to 2. That would be y to the 4th plus 2y squared. And then we get plus 1 minus 1, right? And 1 minus 1 is 0. Just like some of you perhaps mumbled under your breath, I couldn't tell. All right, so antiderivative. We got a pi out front. Y to the 4th gives us 1/5 y to the 5th. And then we have plus, for 2y squared, we get 2/3 y cubed, 0 to 2. That was so short. I could fit it in. If I plug in, that's going to be 2 to the 5th, so 32 over 5, plus 2 to the 3rd is 8, so that's 16/3, and then minus, if I plug in 0, the whole thing zeroes out, right? And what do you get? Yes. (176 pi over 15 units cubed). So the same region revolved in different ways makes different shapes that have different volumes. Is that okay? All right. So at last, I think we're ready for the rings. Which unfortunately the book doesn't call rings, it calls shells. So 6.2, volumes using cylindrical shells. So if we take a region and we revolve it around, if we slice parallel, right, those slices are going to make those ring shapes. Right? Now, the way that this is filling up the volume, you might think of like those Russian dolls where you get the little inside the big inside the big. You're filling this volume up with these rings, right? If we look at a second example, here's a ring that's generated. Or here's another example, right, generating rings. So in each of these cases, we're creating the wall of a right circular cylinder, right? So how this works is I do area times thickness. That's how volume works, right? So when we're talking about area, we're now talking about the surface area of that right circular cylinder's wall, right? So let's think about how the area of a right circular cylinder works. What's it going to be? Well, the perimeter of a circle is its circumference. Yeah. I mean, it's the same thing. They just give it a fancier name for a circle. So that perimeter around, that's the circumference, which is 2 pi r. times the height. So the surface area for the walls of a right circular cylinder is 2 pi r h, right, where r is the radius and h is the height. Is that true? Then for shell method, volume is area times thickness that we integrate, right? So that would be a 2 pi, which I can put in front. I wonder if I spelled height right. I used to be good at English, and then other languages ruined English for me, at least spelling-wise. So, 2 pi radius height. That's how you work with the sides of a cylinder, which is what these rings are. Or they call them shells. Right? I don't care what you call them. I care if you can do them. All right? So this means if I'm going to use shells to fill up the volume instead of discs or washers, what two pieces of information do I need? Radius, which is going to come from the center, and height, which is going to be the length that the shell stretches, right? Okay. So let's say that we look at a given picture here. All right, so we have a region, we're revolving it about the x-axis, and they've forced us to choose horizontal slicing. But that horizontal slicing means when we revolve that around the x-axis, we generate shells. Those rings, like ring for your finger, they're calling those shells. All right? So if I picture it, there's that particular shell that's generated. Of course, I'd fill up that whole region with those lines, which would fill up the whole volume of shells, right? So this is going to be this shape three-dimensionally. And I'm filling it up with shells. Okay. So what is my thickness here? Thickness is dy. For a shell, we have a radius and a height. Now it's important to kind of consider where everything is here. So the radius is going to come out from the center of revolution, right? So the radius is going to be from the center of revolution out to the shell wall. You guys agree? So I've drawn here that this little orange line, that's from the center of revolution out to the shell wall. All right? What is that radius? This is definitely so easy it's hard. How do I need to think about this integral in terms of y? So what is the length of that orange line? Y. That's it. The radius is y. All right? If we want y minus 0. The radius is y minus 0. Remember, that little line that they've drawn here, that's just one shell. How many shells are we filling up this volume with? Infinitely many. Everywhere in that blue region, you're generating a shell. So the radius is going to be whatever the y value is in this case. Does that make sense? All right. What if I generate the shell from up here? All right, you guys told me square root of 2, but neither one of these pictured are square root of 2. They're both smaller than that. Square root of 2 is only when I reach here, that last shell. I also have a little shell right here. Right? Infinitely many shells. Think of those Russian dolls. Dolls within dolls within dolls. Shells within shells within shells. All right? Now, the height of the shell, that would be this length here that it stretches. Right? Remember, I drew the shell for you before, but I guess short-term memory. There's that shell. So that's why the orange is the radius of the shell. And then along this side is the height of the shell. You guys agree? But what is that? Y squared minus 0. Right? It's always big minus little. So for that vertical orange line, the top value is y, the bottom value is 0. And for that horizontal line, big minus little means right minus left. That's y squared minus 0. So our volume here, we've got 2 pi, and then radius times height. That's simply going to be y times y squared dy. My limits of integration, zero to root 2. Here's where your little love for square root of 2 can come back and be appropriate love. 0 to square root of 2. So you got 2 pi, integral from 0 to square root of 2, y cubed dy, right? Antiderivative of y cubed? We got 1/4 y to the 4th. Now, if I pull that 4th out front, that winds up being a pi over 2, right? And then I'm just plugging into y to the 4th. What's the square root of 2 raised to the 4th power? 2 to the 4 halves, which is 2 squared, which is 4. And 0 is 0. So what do we wind up with? Two pi cubic units. All right. What if we had sliced vertically? What would have happened here? We would have made washers. Right? Now, in theory, you can slice either way, right, and use either method that results. In practice, sometimes one method is going to work much better than another, right, for a couple of reasons. Either the integral you set up is way nasty one way, or the equations themselves are too nasty to solve for in the first place. Right? Now, these are relatively easy. We could have done them either way. Okay. Let's try another one. What if we look at y equals x cubed, y equals 8, x equals 0, let's revolve about y-axis. X equals 3. Y equals -1. And x equals -2. Why not? I'm just going to pile them on. All right? All right. You're going to get maximum mileage out of this graph. All right, so my intersections. You guys help me out with that. 0, 8's the easy one. If you plug in 0 for x, you also get 0, 0. If I plug in 8 for y, I get 2. So 2, 8. So y equals 8 is horizontal, x equals 0 is vertical, and of course y equals x cubed is the snake, right? One of my finer graphs. So we'll start out. Spinning around the y-axis. Now, how would you slice this if you wanted discs? Slice horizontally and you'll make discs. If we want shells, slice vertically. Do you see how the horizontal slice would spin around and make a disc? Whereas the vertical slice spins around and makes that ring, right? That shell. We're doing the shell method, so let's do the shell method. All right? But for funsies, if you find yourself bored over the weekend, you can go back and do the disc and get the same answer. So your thickness here would be dx if we're doing shell method, right? Slicing vertically, we get dx. And what do we need for shells? We need the radius and height of the shell. So that's what the shell that I drew the little blue line for would look like. That's what the shell in that particular case would look like. So the radius, that's got to go from the center to the outer wall of the shell, right? So what is your radius there? The radius is much easier than you think. It's a shell, so it's going to have the radius is going to be the same all the way up and down the y value. So what's going to change depends on x. So it's x minus 0.
It's always x, well, x or y, depending on if it's dy or dx.
Well, minus something.
Okay. Right.
Whereas the height of the shell, that would be along this wall right up here. What's that going to be? Eight minus x cubed. It's always big minus little. These are all big minus little. Right? They all are big minus little. It's just if you're looking at that horizontal piece, that's right minus left. Right? If you're looking for a vertical piece, it's top minus bottom. And we want everything in terms of x because it's a dx integral. You got to keep your mind in the mindset of whichever differential you chose. All right? So volume for a shell method is 2 pi times radius times height. So it's going to be 2 pi times x times 8 minus x cubed dx. Radius times height, 2 pi. Your limits of integration, they got to be x values, so 0 to 2. So this is 2 pi, integral from 0 to 2, of 8x minus x to the 4th dx. You guys agree? So 2 pi, antiderivative of 8x, 4x squared, and then minus, for x to the 4th, that's 1/5 x to the 5th. Going from 0 to 2. So that's 2 pi, that's going to be 16 minus 32 fifths. And then if I plug in 0, the whole thing is 0 for the back half. Now for this one, do not forget the 2 out front. That's a common careless mistake. It's a 2 pi out front, unlike the other 2. And you wind up with 96 pi fifths. Cubic units. Where do we go next? Around the line x equals 3. So same region, but now we're spinning around the line x equals 3. Again, this is the shell section, so let's do shells. Slice vertically or horizontally for shells? Slice vertically for shells. If I slice horizontally, what would I create? I would create washers. Do you guys see? Are you starting to see? Picture in your mind's eye. Horizontal would slide around and make washers. Vertical, as you slide them around, you'd make those rings, right? So if I just kind of pictured this one shell that I've demonstrated here, and there's what that shell would look like. Okay. Your thickness here would be dx. That means everything's got to be in terms of x. And for shells, you need radius and height. All right, so the radius, that's going to come from the center of the shell out to the outer wall, right? So what is this right here? You got it. Your radius is 3 minus x. Right? For a little horizontal slice there, big minus little means right minus left. Right minus left. That is 3 minus whatever the x value is. 3 minus x. Meanwhile, the height of the shell would be the side wall, right? What's that going to be? 8 minus x cubed. You guys agree? So I didn't actually draw the three-dimensional shape that we were creating. And this is the three-dimensional shape that we would create. And we're filling that with shells. This was the one shell that I drew. but we're filling that whole region with shells. So volume, 2 pi, radius, height. So that would wind up being 3 minus x times 8 minus x cubed, right? My limits of integration, you got to be x values, right? So it's going to go from 0 to 2. Now we definitely can't integrate that, so what do I have to do? FOIL it out. So we got 2 pi, integral 0 to 2. That'll be 24 minus 8x minus 3x cubed plus x to the 4th dx. How'd I FOIL? Like a champ? Well, good. All of those we can find the antiderivative of. 24, 24x. Minus 8x,
Negative 4x squared.
minus 4x squared. Minus 3x cubed,
Negative 3/4 x to the 4th.
negative 3/4 x to the 4th. Plus x to the 4th,
X over 5.
that's fine. You can do x to the 5th over 5 or 1/5 x to the 5th. All right? Fraction Hades on this one. So I got a 2 pi outside, and when I plug in, that winds up being a 48 minus 16 minus 12 plus 32 fifths. And then if I plug in 0, we just get 0. You guys agree? And what kind of damage have we done here? I got 264 pi fifths. You guys back me up? Cubic units. Let's actually get a little more interesting with this. For the next one, what do I do? Y equals negative 1. Because I know you're allergic to negatives, so I wanted to throw a couple in there. So y equals negative 1 means I'm revolving around this axis. So how do I slice if I want to make shells?
Parallel to
Yep.
what you're saying.
So just picture this little horizontal line. If I spin that around, y equals negative 1, I generate those ring shapes. Can you guys visualize? Right? What would happen if I'd sliced vertically? I would have created washers. Right? So if we're going to go with shells, and I forced you to, so this would look like oh. The shape. All right. What's your thickness? Your thickness is dy, which means everything's got to be in terms of y. So that means this y equals x cubed graph we would need to rethink as x equals cube root of y, or x equals y to the 1/3. Okay. And for shells, we need radius and height. All right, so this representative shell that I drew, the radius, you've got to come from the center of revolution out to the shell wall. So what is your radius going to be? Y minus negative 1, which is y plus 1. Whereas the height would have to be this side wall, right? So what is this height right here? Y to the 1/3 minus 0, which is just y to the 1/3. You guys okay with that? So tell me my volume formula. How do I put this together? 2 pi radius times height would be y plus 1 times y to the 1/3 dy. Do not leave off your dy. What about my limits of integration? 0 to 8. They got to be y values. So it's going to be 0 to 8. All right, so we got 2 pi integral 0 to 8. I'll distribute y to the 1/3. So that's y to the 4/3 plus y to the 1/3 dy. That we can do the antiderivative of. Not that it's the nicest, but what do I get for y to the 4/3? We get y to the 7/3 with the 3/7 thrown out front. Plus, this would be y to the 4/3 with 3/4 thrown out front. You guys agree? So that's a 2 pi. Let's see, if I plug in 8. Now, that fractional 3 in the power means a cube root, and the cube root of 8 is 2. So I want 2 to the 7th. 128? And 128 times 3/7. Well, I'm out. Look, it's just 3/7 times 128. Then we've got plus 3/4. Cube root of 8 is 2. 2 to the 4th is 16. Oh, that's just going to be 12. Minus 0. Was it 384 over 7? All right. Redeemed myself slightly. So we wind up with, if I did my math right, 936 pi over 7.
Yes.
Cubic units. I think I just had one more for you guys. X equals -2, right? All right, let's check it out. So x equals -2. This would be my axis of revolution out to the side. If I want to generate shells, I would slice vertically. Vertical slices would make shells. Picture it. Whereas a horizontal slice would have made washers. Right? Thickness here? dx. Radius and height then?
Plus 2.
So remember, the radius comes from the center of revolution out to the shell wall. X minus negative 2. Which is x plus 2. Whereas the height would be the length of the wall itself, which is 8 minus x cubed. Is that okay? Do you guys see how we're getting that? I've shelled you to death. You're shell shocked. Oh. I didn't plan that one. It just kind of slipped out. All right, so 2 pi, radius times height, x plus 2, times 8 minus x cubed dx. Your limits of integration? 0 to 2. We can't integrate that, so we'll multiply it all out first. 2 pi, integral 0 to 2. That would be 16 plus 8x minus 2x cubed minus x to the 4th. Did I get them all? dx. Pokemath. Got to get them all. Two pi and we anti-differentiate. That's 16x plus 4x squared minus 1/2 x to the 4th minus 1/5 x to the 5th. And we were relatively getting not too bad numbers until that last one. So we've got 2 pi. 32 plus 16 minus half of 16 is 8 minus 32 over 5. So there's one bad apple in the bunch, right? There's one in here, that's for sure. And then if you plug in 0, that all works nicely. And what do we get? I think I started to hear it whispered from somebody. (576 pi sevenths) cubic units. At this point, I'll just call it u cubed, and you have to figure out that that's units. I ran out of room. All right. 336 pi over 5 units cubed.